Well, this is electric circuits course, second semester, offered in spring 2020 to the students of Department of Electrical Engineering at UT Lahore, and I am Dr. Khalid M. Hassan. This is our textbook. I have mentioned 8th edition, but if someone have earlier edition, it will be okay. Our today's discussion is on maximum signal transfer. Uh, the same topic comes with the maximum power transfer heading, maximum power transfer. Both have same meaning. In the textbook, it is chapter 3 and section 3.5. Duration of this lecture will be short as I have written a lot of stuff before its recording. Now, in maximum power transfer or maximum signal transfer, we see that when a source is fixed, how the power delivered to the load will be varying. Fixed source means there is no change in the source, and at present the source is represented by its Thevenin equivalent, only two elements, but the actual source may consist of several voltage sources, current sources, and resistors. And here we are discussing a case when source is fixed. Nothing can be changed in the source, and we can change the load only. And the load can be changed by using adjustable resistor. Now, the source circuit, which is to the left of this red line, and the load, which is shown over here, we will see how load voltage will vary, how load current will vary, and how the power delivered to this load resistance will be varying by varying the load. We will also see another parameter, which is power efficiency. Now, as the load is fixed, as the source is fixed, Vt and Rt are fixed. We can vary only RL. And due to variation in RL, we want to see variation in load voltage, variation in load current, and variation in power output. And due to variation in power output, we will also explore what is the value of the load resistance for which the maximum power is delivered to the load. We also see the power efficiency, which is output power divided by the input power. Now I will reproduce the circuit. I have reproduced the circuit here again, as it is a single loop in Thevenin equivalent. So current I is flowing as indicated in this direction. We see that the voltage output here, look at the circuit diagram, voltage over here across the load, this is equal to the current flowing through the load multiplied by the load resistance. So this is the voltage. Current flowing through the load means the mesh current in this case is the voltage divided by sum of these two resistances. As the power is product of voltage and current, we see that the final expression of the power is RL Vt square over RL plus RT square. Now we would like to see under what condition means value of RL output power will be maximum. I will say again, we will explore a value of RL for which the power delivered to the output means to the load is maximum. We have got the function of power over here. So this is a mathematical method to find the maximum value of a function by differentiating the function with respect to a variable. In here, our variable is load resistance. So we differentiate power with respect to RL. And if we differentiate PO and then we equate it to 0, it means we are looking at the zero rate of change, when there is no rate of change in the power. dPO divided by dRL equal to 0 means when the rate of change is 0. We will see again that if on horizontal axis we have RL and over here we have PO, the shape of PO will be more like that. This is the shape of the power output. Now if we see what is rate of change of power during this segment and then the next segment and then the next segment, or if we see point wise over here, rate of change, rate of change, rate of change, rate of change, we see that rate of change is much higher as compared to the rate of change over here. And finally at the peak, it is the rate of change with respect to RL is 0 over here, and this is the maximum value. We equate it to 0 and then we find a value of RL for which we will have maximum power output, and due to this differentiation we get RL equal to RT. It means that when our load resistance is equal to the Thevenin resistance of the source, maximum power will be delivered. In order to find the value of maximum power, we apply this condition of RL equal to RT in the power output expression in order to see what is the maximum power. So we have finally, in its final form, the maximum power is Thevenin voltage square divided by 4RT. As you know, the Thevenin voltage can also be expressed as the product of Norton current and the resistance, Norton resistance, or we can say Thevenin resistance, because Norton and Thevenin resistance are same. we can express the maximum power output as IN square multiplied by IT divided by 4. Also note that VO maximum of the source is I'm using the letter V for the load voltage. Therefore, V maximum is V open circuit, it is the Thevenin voltage, and I maximum is I short circuit, which is I Norton. I'll repeat again. The source, which is VT and RT, when we remove the load, when there is no load, this voltage is open circuit voltage, and this is the maximum value of voltage which we can have at this pair of terminal. So this is Thevenin voltage. This voltage, Thevenin voltage, will appear at the output because there is no current and there is no voltage drop across this resistance. And what is the current? Maximum current. Maximum current we achieve when we short circuit this pair of terminal. So the current flowing through this mesh will be short circuit current, and which is short circuit current is equal to VT divided by RT. As you know, VT is, we have said before, VT is INRT divided by RT. See my previous lecture for the derivation of this VT equal to INRT. So here we see that I maximum is I short circuit, which is the Norton current. The fourth parameter we see is the power efficiency, output power divided by the input power. What is output power? Output power is the voltage across the load multiplied by the current which is flowing through the load, and we have already seen it. What is input power? Means the power delivered by the source circuit, and our source circuit is represented by its Thevenin equivalent, and there is only one source, which is the Thevenin voltage source, multiplied by the current. Look at the circuit diagram. The current flowing through it is I, and the current is I, but not in this case. Is at present it is I short circuit. So if we have a load over here, then the current is I and this voltage is V. So I was saying that PI input, at the input side, the source side, the voltage multiplied by its current, it is the power delivered by the voltage source or the source circuit, VT, multiplied by I, and it is VT square divided by RL plus RT. Now the efficiency, as we have defined the power efficiency as the ratio of P output to the PA input, we see that finally we have efficiency equal to RL plus RT. We will also see efficiency when RL, what is the efficiency when RL is equal to RT and maximum power is delivered to the load. Here, if we see above, this is the condition is equal to RT, which ensures the maximum power output. We substitute here RL is equal to RT, and we will see that this power efficiency is equal to 1 by 2, or in percentage this is 50% power efficiency. This is very strange thing. You may be thinking that when maximum power is delivered to the load, power efficiency is maximum, but here when maximum power is delivered to the load, power efficiency is only 50%. Now, as engineers or scientists, we all use the plots and curves in order to draw variables against some independent variables to have a pictorial view of what is happening in a system or in some circuit. We plot output power divided by its maximum value. The voltage across the load divided by its maximum value, which is maximum output voltage is open circuit voltage. We also draw current divided by its maximum value of current. Now, when we divide all the values of a variable by its maximum value, then the resulting values are known as normalized values. And in such a case, a variable divided by its maximum value will be 1. The maximum value of PO divided by PO maximum is 1. The maximum value of V, voltage divided by its maximum value, is 1. Similarly, the maximum value of I divided by its maximum value is 1. This is normalized way to show curves. Now, we see that at the horizontal axis, instead of RL, we use RL divided by RT. This is the preferred method to visualize things in a better way. What does it mean? When RL divided by RT is equal to 1 here, it means that RL is equal to RT. So over here you will see RL is 4 times RT. So we have shown, we have gone up to the maximum 4 times RT, but here if we want to extend the range of RL over RT, say over here, if we extend it when RL is equal to 11 times RT, we see that the peak over here in the previous graph is shifted toward the vertical axis, and if we move further, this peak, the peak over here, will be shifted further towards the vertical axis, and it may not be visible clearly. Now, in order to see a wide range of RL over RT, we use a logarithmic scale on the horizontal axis to cover a broader range of RL over RT. Now, what is the logarithmic scale? You see, this value is 10 raised to the power 0, and the next is 10 raised to the power 1, and the next is 10 raised to the power 2. Similarly, if we move backward, it is 10 raised to the power minus 1, which is 0.1, and 10 raised to the power minus 2, which is 0.01. So you see in here we can see all 3 curves, normalized values of curves with normalized value in a better way. And if we adjust this 1 ratio of RL over RT here, so at this point RL is equal to RT, we can visualize it better, we can see it clearly. Interestingly, at this point, when maximum power is delivered to the load, the voltage and current is not maximum. It is over here, and we will see that when the power output is maximum, the voltage is 50% of its maximum value, and the current flowing through the load is also 50% to the maximum value. So it is shown over here. When RL is equal to RT, power output is maximum, and interestingly, when RL is equal to RT, the voltage, this is the previous expression of the voltage. If we substitute RL equal to RT, the voltage is VT divided by 2. We know that VT is the maximum output voltage, which is the open circuit voltage. So it is the 50% of the maximum available output voltage. Now the current, we already know the expression of the current. We substitute RL equal to RT, and we will see that it is VT divided by 2 RT, and finally it is 50% of I short circuit, and I short circuit is the maximum value of the current in the mesh. Remember, it is I short circuit over here is the previous expression you can see over here. I short circuit is IN, and VT is INRT. So VT over here, as VT is INRT, you know IN, Norton current, is the short circuit current. So if we substitute it over here, we will have I short circuit or I Norton or I maximum divided by 2. Now, as for maximum power output, we substitute RL equal to RT, and at RL equal to RT, what is the voltage? The voltage is VO divided by C 2, and the current is I short circuit divided by 2, and we can express the maximum output power in this expression as well. There are a lot of examples which can be discussed, but it is a short lecture. Today's lecture is a short lecture. I will present only one example, and in this example, values of all the resistors and current source is mentioned, but the load, which is over here, this is the load. This is our load. Instead of single resistor, it is possible that we have multiple resistors in series parallel combination. Say this resistance is 12K, and this resistance, as 12K means fixed, and this resistance R, it can be varied. We will see what is the value of this R for which the maximum power will be delivered to the load. So for this, we first find the Thevenin equivalent of the source over here. So the Thevenin equivalent of the source will be, we can use Norton equivalent of the source circuit. Results will be same. So this is a pair of terminals A and B. So I hope that you should be able to find the Thevenin equivalent of the source circuit. And then we already know that what is the maximum output power when RL is equal to RT, or we can use VT square divided by 4 RT, or we can use this expression, or we can use this expression. So just as a reminder, I have shown RT is V open circuit divided by I short circuit. We can use, remember, we can also find RT due to open circuit voltage and short circuit current, or by circuit reduction methods. Circuit reduction method means in the given circuit at present the circuit reduction applies only to circuits where we have all independent sources. Now in the circuit reduction we remove all the sources, and as it is a current source 50 milliampere we have removed, means we open circuit this to make the current zero, and then we redraw the remaining circuit, and this is a pair of terminals A and B, and in order to see R Thevenin seen through this pair of terminal, so RT is the equivalent resistance. So at present all three resistances are in series, so 3 to 5, and so this is 6K. Now we know what is RT, we can find what is VT, and knowing RT, RL should be equal to RT, and this is known. And what is RL? RL is, if you see the circuit diagram, RL is the parallel combination of 12K resistance and R. This is 12,000 R divided by 12,000 plus R, and if RT is 6K means 6,000, we can find R easily. More examples can be discussed, but I hope that as you have listened my previous lectures on two lectures on Thevenin equivalent and Norton equivalent circuits, you can attempt most of the related end problems in the textbook. That's it. Thank you very much.